The structure of the atom is one of the most important ideas in understanding the nature of matter, because it explains how everything in the universe is built at the most fundamental level. For a long time in human history, people believed that matter was continuous and could be divided endlessly into smaller pieces. Ancient philosophers like Democritus suggested that matter was made of tiny, indivisible units called atomos, meaning uncuttable. Although this idea was philosophical rather than scientific, it laid the foundation for modern atomic theory. Today, science has revealed that atoms are not indivisible, but they do represent the basic units that define the properties of elements and substances. An atom is incredibly small, far too small to be seen even with powerful optical microscopes. To understand its structure, scientists developed models based on experiments, observations, and mathematical theories. These models evolved over time as new discoveries were made. Early scientific models imagined atoms as solid spheres, much like tiny billiard balls. This view changed dramatically as scientists began to uncover the internal structure of the atom and the particles that exist inside it. At the center of every atom is a dense core known as the nucleus. The nucleus is extremely small compared to the overall size of the atom, yet it contains almost all of the atom's mass. This means that most of an atom is actually empty space. If an atom were enlarged to the size of a stadium, the nucleus would be no bigger than a marble at the center, while the electrons would occupy the space throughout the stadium. This comparison helps illustrate just how tiny and concentrated the nucleus really is. Inside the nucleus are two types of particles, protons and neutrons. Protons carry a positive electric charge while neutrons have no charge at all. Despite having no charge, neutrons play a crucial role in the stability of the nucleus. Protons naturally repel one another because like charges repel, but the presence of neutrons helps hold the nucleus together by contributing to the strong nuclear force. This force is one of the fundamental forces of nature and is powerful enough to overcome the repulsion between positively charged protons at very short distances. The number of protons in the nucleus is what defines an element. For example, hydrogen atoms always have one proton, carbon atoms have 6 protons, and oxygen atoms have 8 protons. This number, known as the atomic number, determines the chemical identity of the atom. Changing the number of protons changes the element itself. No matter how many neutrons or electrons an atom has, if it has 6 protons, it is always carbon. Surrounding the nucleus are electrons, which are much smaller and lighter than protons and neutrons. Electrons carry a negative electric charge and move around the nucleus in regions called electron clouds. Unlike planets orbiting the Sun in neat, circular paths, electrons do not follow fixed or predictable orbits. Instead, their positions are described by probability. Scientists can calculate the likelihood of finding an electron in a certain region around the nucleus, but they cannot pinpoint its exact location at a given moment. This concept comes from quantum mechanics, a branch of physics that governs the behavior of particles at extremely small scales. The arrangement of electrons around the nucleus follows specific energy levels. These energy levels determine how tightly electrons are bound to the atom. Electrons closer to the nucleus have lower energy and are held more tightly, while electrons farther away have higher energy and can be more easily removed or shared with other atoms. This structure explains why some atoms are more reactive than others. Atoms with electrons that are loosely held in their outer regions are more likely to participate in chemical reactions. The outermost electrons of an atom are especially important because they determine how atoms interact with each other. When atoms bond to form molecules, it is the electrons that are involved in these interactions. Atoms may share electrons, lose electrons, or gain electrons in order to achieve a more stable arrangement. This behavior is directly related to the structure of the atom and the way its electrons are organized. One of the most significant discoveries about atomic structure came from experiments involving the scattering of particles. In the early 20th century, scientists fired positively charged particles at thin sheets of gold. They expected the particles to pass straight through if atoms were solid throughout. Instead, some particles were deflected at sharp angles, and a few even bounced back. This surprising result led to the conclusion that atoms have a small, dense, positively charged nucleus, with most of the atom being empty space. This experiment fundamentally changed our understanding of atomic structure. As scientific tools improved, so did atomic models. The development of quantum theory revealed that electrons behave both like particles and waves. This wave-particle duality explains why electrons do not spiral into the nucleus despite being attracted to the positively charged protons. Instead, electrons exist in stable energy states that prevent them from collapsing into the nucleus. This balance between attraction and energy is a key feature of atomic structure. The structure of the atom also explains why atoms have mass. Protons and neutrons are much heavier than electrons, so they contribute nearly all of the atom's mass. Even though electrons are essential for chemical behavior and electrical charge, their mass is so small that it is often considered negligible in comparison. This is why the mass of an atom is concentrated in its nucleus. Different atoms of the same element can have different numbers of neutrons. These variations are called isotopes. Isotopes have the same number of protons and electrons, so they behave the same chemically, but they have different masses because of the differing number of neutrons. This aspect of atomic structure is important in fields such as medicine, archaeology, and energy production, where isotopes are used for imaging, dating ancient artifacts, and generating nuclear power. Understanding atomic structure also helps explain why atoms can be stable or unstable. Some combinations of protons and neutrons form stable nuclei that can exist indefinitely, while others are unstable and undergo radioactive decay. In radioactive atoms, the nucleus changes over time, releasing energy and particles as it transforms into a more stable form. This process again highlights the importance of the nucleus in the overall structure of the atom. The structure of the atom is not just a theoretical concept, it has practical consequences in everyday life. The materials we use, the energy we generate, and the technology we rely on all depend on atomic structure. Semiconductors in electronic devices work because of the way electrons move through atomic structures. Nuclear energy is produced by changes within atomic nuclei. Even the colors we see are related to how electrons move between energy levels within atoms. In essence, the atom is a complex and dynamic system rather than a simple, solid object. Its structure consists of a dense nucleus made of protons and neutrons, surrounded by electrons that exist in probabilistic regions governed by quantum laws. This structure explains the mass, stability, reactivity, and electrical behavior of matter. By understanding the structure of the atom, we gain insight into why matter behaves the way it does and how the fundamental building blocks of the universe are organized. This knowledge forms the foundation for exploring deeper questions about atomic charges, chemical bonding, and the forces that hold the material world together. As scientific understanding deepened, the structure of the atom came to be seen not as a static arrangement of particles, but as a dynamic system governed by forces and probabilities. One of the most remarkable aspects of atomic structure is the balance of forces that keeps the atom stable. Positively charged protons in the nucleus repel one another, yet the nucleus does not fly apart under normal conditions. This stability exists because of the strong nuclear force, an extremely powerful force that acts only over very short distances. It binds protons and neutrons together so tightly that it overcomes the electrical repulsion between protons. Without this force, atoms as we know them could not exist, and matter would have no stable foundation. At the same time, another balance exists between the nucleus and the electrons surrounding it. Electrons are attracted to the nucleus because opposite charges attract. Classical physics once suggested that electrons should spiral inward and collapse into the nucleus, much like a satellite losing energy and falling toward a planet. However, this does not happen. Quantum mechanics explains that electrons can only exist at specific energy levels. These energy levels act like steps on a ladder rather than a smooth slope. As long as electrons remain within these allowed levels, the atom remains stable. This idea transformed the understanding of atomic structure and showed that the microscopic world behaves very differently from the everyday world we experience. The electron cloud model further refined the picture of atomic structure. Instead of imagining electrons as tiny dots moving along precise paths, scientists now describe them as existing in clouds of probability. These clouds represent regions where an electron is most likely to be found. Some clouds are spherical, while others have more complex shapes, depending on the energy and motion of the electrons. These shapes are not random, they are determined by mathematical equations that describe electron behavior. The complexity of these electron distributions helps explain the wide variety of chemical behaviors seen among different elements. Atomic structure also explains why elements are arranged the way they are in the periodic table. The periodic table is not just a list of elements, it is a map of atomic structure. Elements are arranged according to the number of protons in their nuclei and the arrangement of their electrons. Patterns emerge because atoms with similar electron structures behave in similar ways. For example, elements in the same column of the periodic table often have similar chemical properties because they have the same number of electrons in their outermost regions. This repeating pattern reflects the underlying structure of atoms and the way electrons fill available energy levels. As atoms grow larger, their structures become more complex. Heavier atoms have more protons and neutrons in their nuclei and more electrons in their surrounding clouds. With more electrons come more energy levels and more possible interactions. This complexity leads to a greater variety of chemical behaviors and bonding possibilities. Some atoms readily form bonds with many other atoms, while others are relatively inert. These differences are not random, they arise directly from atomic structure and the arrangement of electrons. The structure of the atom also helps explain the concept of atomic size. Atomic size is not determined by the nucleus, which remains extremely small even in large atoms, but by the reach of the electron cloud. Atoms with electrons that occupy higher energy levels tend to be larger because their electron clouds extend farther from the nucleus. This variation in size affects how atoms pack together in solids, how they interact in chemical reactions, and how they form molecules. Once again, a seemingly abstract feature of atomic structure has tangible effects in the physical world. Another important aspect of atomic structure is the idea of energy transitions. Electrons can move between energy levels by absorbing or releasing energy. When an electron absorbs energy, it can jump to a higher energy level farther from the nucleus. When it returns to a lower energy level, it releases energy, often in the form of light. This process explains the origin of atomic spectra, which are unique patterns of light emitted or absorbed by different elements. These spectra act like atomic fingerprints, allowing scientists to identify elements in distant stars and galaxies. Through atomic structure, humans have been able to study the composition of the universe far beyond Earth. Atomic structure is also deeply connected to the concept of charge, which lies at the heart of matter's behavior. While the nucleus provides positive charge through protons, the electrons provide negative charge. The spatial separation between these charges and the ability of electrons to move make electrical phenomena possible. In solids, especially metals, electrons can move relatively freely through atomic structures, allowing electric current to flow. In other materials, electrons are more tightly bound, leading to insulating behavior. These differences arise not from the charges themselves, but from how atomic structure organizes those charges. In extreme conditions, atomic structure can change dramatically. Under high temperatures or intense radiation, electrons can be stripped away from atoms, creating a state of matter known as plasma. In plasma, the usual structure of atoms breaks down, and charged particles move freely. This state of matter exists naturally in stars, including the Sun, and plays a crucial role in astrophysical processes. Understanding atomic structure allows scientists to explain how matter behaves under such extreme conditions and how energy is generated in stars. The nucleus itself can also undergo changes that alter atomic structure. In nuclear reactions, the number of protons or neutrons in a nucleus can change, transforming one element into another. This process releases enormous amounts of energy, far greater than that released in chemical reactions. Nuclear power plants and nuclear weapons both rely on these changes in atomic structure. While chemical reactions involve the rearrangement of electrons, nuclear reactions involve the rearrangement of the nucleus, highlighting the layered complexity of atomic structure. Atomic structure has also shaped modern technology and medicine. Techniques such as X-ray imaging, magnetic resonance imaging, and radiation therapy all rely on interactions with atomic particles. These technologies work because scientists understand how electrons and nuclei respond to energy and fields. Even the development of lasers depends on precise control of electron energy transitions within atoms. What once seemed like an abstract scientific curiosity has become a foundation for life-saving and world-changing innovations. Ultimately, the structure of the atom reveals that matter is not solid or simple, but deeply intricate and governed by fundamental laws. Atoms are composed of tiny particles held together by powerful forces and balanced by precise energy rules. Their structure determines how they interact, how they combine, and how they respond to energy. By uncovering the structure of the atom, science has provided a coherent explanation for the behavior of matter at every scale, from the smallest particles to the largest structures in the universe. This understanding prepares the ground for exploring why atoms carry charges and how those charges influence everything from the stability of matter to the forces that shape our world. The story of protons, electrons, and neutrons is essentially the story of how matter is built and how it behaves at the most fundamental level. These three particles form the core of atomic structure, and understanding them allows us to explain why atoms exist, why they are stable, and why they interact in specific ways. Although atoms appear simple from the outside, they are actually complex systems made possible by the unique properties of these subatomic particles. Protons are one of the most important particles in an atom because they define the identity of an element. Every proton carries a positive electric charge, and this charge is identical in strength for all protons everywhere in the universe. What makes protons special is not just their charge, but also their mass and location. Protons are found in the nucleus at the center of the atom, tightly packed together with neutrons. Compared to electrons, protons are relatively heavy, having a mass about 136 times greater than that of an electron. This large mass means that protons contribute significantly to the overall mass of the atom. The number of protons in an atom determines what element that atom is. This number is known as the atomic number. For example, hydrogen atoms always have one proton, helium atoms always have 2 protons, and carbon atoms always have 6 protons. If the number of protons changes, the atom becomes a different element entirely. This makes protons fundamental to chemistry and physics, as they define the basic categories of matter found in the periodic table. Because protons carry positive charge, they naturally repel each other. Under normal circumstances, like charges push away from one another, this raises an important question. How can multiple protons exist so close together inside the nucleus without flying apart? The answer lies in another powerful interaction known as the strong nuclear force. This force acts over extremely short distances and is much stronger than the electric repulsion between protons. It effectively binds protons together within the nucleus, allowing atoms to exist at all. Neutrons are the second major particle found in the nucleus. Unlike protons, neutrons carry no electric charge, which is why they are called neutral particles. Despite lacking charge, neutrons play a crucial role in atomic stability. They help hold the nucleus together by contributing to the strong nuclear force. In many atoms, The presence of neutrons reduces the repulsion between protons by spacing them slightly apart, making the nucleus more stable. Neutrons have a mass very similar to that of protons, slightly heavier in fact. Because of this, neutrons also contribute significantly to the mass of the atom. While protons determine the identity of an element, neutrons influence the stability of that element. Atoms of the same element can have different numbers of neutrons, resulting in different forms known as isotopes. These isotopes behave almost identically in chemical reactions because their electron structures are the same, but they differ in mass and nuclear stability. Some isotopes are stable and exist naturally, while others are unstable and radioactive. In unstable nuclei, the balance between protons and neutrons is not ideal. Over time, these nuclei release energy and particles in an attempt to reach a more stable configuration. This process, known as radioactive decay, is another direct consequence of the relationship between protons and neutrons within the nucleus. Electrons are the third major subatomic particle and are very different from protons and neutrons in several ways. Electrons carry a negative electric charge, equal in magnitude but opposite in sign to the positive charge of protons. This balance of charge is what allows atoms to be electrically neutral when they have equal numbers of protons and electrons. Electrons are much smaller and lighter than protons and neutrons, and their mass is so small that it contributes very little to the total mass of the atom. Electrons are not found in the nucleus. Instead, they exist in regions around the nucleus known as electron clouds. These regions are not fixed paths but areas where electrons are most likely to be found. The behavior of electrons cannot be fully explained by classical physics. Instead, it is described by quantum mechanics, which shows that electrons exhibit both particle-like and wave-like properties. This dual nature is one of the most fascinating aspects of electrons. Because electrons are negatively charged, they are attracted to the positively charged nucleus. This attraction is what keeps electrons bound to the atom. However, electrons do not collapse into the nucleus because they occupy specific energy levels. These energy levels act as stable states that electrons can occupy without losing energy. As long as electrons remain in these allowed states, the atom remains stable. The arrangement of electrons around the nucleus plays a major role in determining how atoms interact with one another. The outermost electrons, often called valence electrons, are especially important. These electrons are involved in chemical bonding, which is the process by which atoms combine to form molecules. Atoms may share electrons, lose electrons, or gain electrons in order to achieve a more stable electron arrangement. This behavior explains why different elements form different types of bonds and compounds. The interaction between protons and electrons is also responsible for electrical phenomena. When electrons move from one atom to another, an imbalance of charge is created. This imbalance results in static electricity or electric current, depending on the situation. In metals, electrons can move relatively freely, allowing electricity to flow easily. In insulators, electrons are more tightly bound, preventing the flow of electric current. These differences arise directly from the way electrons interact with atomic nuclei. Although neutrons do not participate directly in chemical reactions, their influence on atomic behavior should not be underestimated. By affecting nuclear stability, neutrons indirectly determine whether an atom can exist long enough to participate in chemical processes. In nuclear reactions, changes in the number of neutrons or protons can release enormous amounts of energy. These reactions power stars, including the sun, and have been harnessed by humans for energy production and medical applications. The discovery of protons, electrons, and neutrons was a gradual process that reshaped scientific understanding. Electrons were the first to be discovered, revealing that atoms were not indivisible. Protons were later identified as the source of positive charge within the nucleus. Neutrons were the last to be discovered, solving many puzzles about atomic mass and stability. Together, these discoveries transformed the atom from a simple concept into a detailed and dynamic system. What makes these particles even more remarkable is that they are universal. Every atom in the universe is built from the same types of protons, electrons, and neutrons. The differences between elements arise not from different kinds of particles, but from different numbers and arrangements of the same particles. This universality gives the universe a deep sense of order and consistency. The relationship between protons, electrons, and neutrons explains why atoms have both mass and charge. Protons and neutrons provide mass and nuclear stability, while electrons provide chemical behavior and electrical properties. None of these particles alone could create matter as we know it. It is only through their interaction that atoms can exist, molecules can form, and complex structures can arise. In understanding these three particles, we gain insight into why matter behaves the way it does. The solidity of objects, the flow of electricity, the release of nuclear energy, and even the processes that sustain life all depend on the delicate balance between protons, electrons, and neutrons. Their properties and interactions form the foundation of atomic science and set the stage for exploring deeper questions about charge, bonding, and the forces that govern the universe. The deeper significance of protons, electrons, and neutrons becomes clearer when we consider how their interactions shape both the microscopic and macroscopic worlds. These particles are not merely components of atoms, they are active participants in the forces and the processes that govern matter. Their behavior explains why substances differ from one another, why energy can be stored and released, and why the universe has structure rather than chaos. One of the most striking features of protons and electrons is the exact balance of their electric charges. The positive charge of a proton is equal in magnitude to the negative charge of an electron. This precise balance allows atoms to exist in a neutral state when the numbers of protons and electrons are equal. It also makes it possible for even small changes in electron number to have noticeable effects. When an atom gains or loses just one electron, it becomes an ion with a net charge, dramatically changing how it interacts with other atoms. This sensitivity highlights how crucial electrons are in determining atomic behavior. Electrons, because of their small mass, respond easily to external influences such as electric fields, magnetic fields, and energy input. This responsiveness is what makes modern technology possible. In electronic devices, electric currents are essentially controlled flows of electrons through materials. The ability to manipulate electrons without disturbing the much heavier protons and neutrons allows for precise control of electrical signals. This property stems directly from the fundamental difference in mass and mobility between electrons and the particles in the nucleus. Protons, while less mobile, play a defining role in shaping atomic interactions through their influence on electron arrangement. The positive charge of the nucleus determines how strongly electrons are attracted to an atom. Atoms with more protons exert a stronger pull on their electrons, affecting atomic size, ionization energy, and reactivity. This is why elements with higher atomic numbers often display different chemical behaviors compared to lighter elements. The nucleus, though small, governs the entire structure of the atom through its charge. Neutrons contribute to this picture in a more subtle but equally important way. By adding mass without adding charge, neutrons allow nuclei to be stable across a wide range of sizes. In heavier elements, additional neutrons are necessary to counterbalance the increasing repulsion between protons. Without neutrons, most atoms beyond hydrogen would be unstable. This makes neutrons essential for the existence of the diverse elements found in nature. The role of neutrons becomes especially evident in nuclear processes. In nuclear fission, a heavy nucleus absorbs a neutron and becomes unstable, splitting into smaller nuclei and releasing energy. In nuclear fusion, light nuclei combine to form heavier ones, a process that also depends on the presence and behavior of neutrons. Fusion powers stars, producing the light and heat that make life on Earth possible. These nuclear reactions show that while electrons govern chemistry, protons and neutrons govern the energy of the universe itself. The interactions among these particles also explain why matter has structure at larger scales. Chemical bonds formed through electron interactions allow atoms to link together into molecules. These molecules in turn assemble into solids, liquids, gases, and biological structures. Meanwhile, the stability of atomic nuclei ensures that these structures persist over time. If nuclei were unstable, matter would constantly fall apart, and complex forms such as living organisms could not exist. Another important aspect of protons, electrons, and neutrons is their role in conservation laws. Charge is conserved in all physical processes, meaning the total amount of positive and negative charge remains constant. This conservation is rooted in the fixed charges of protons and electrons. Similarly, the conservation of mass and energy in nuclear and chemical reactions depends on the behavior of protons and neutrons. These principles give the universe predictability and allow scientists to understand and model physical processes accurately. The study of these particles has also expanded human understanding beyond atoms to even smaller scales. Protons and neutrons themselves are made of more fundamental particles called quarks, held together by gluons. While electrons are considered fundamental particles with no known internal structure, protons and neutrons reveal deeper layers of complexity within matter. This discovery shows that the quest to understand matter is ongoing, and that each level of understanding opens the door to new questions. In practical terms, knowledge of protons, electrons, and neutrons has revolutionized medicine, energy, and industry. Medical imaging techniques rely on electron behavior and nuclear properties. Radiation therapy uses controlled nuclear decay to treat cancer. Energy technologies, from batteries to nuclear reactors, depend on precise manipulation of these particles. Each application is a direct result of understanding how these subatomic components behave and interact. Perhaps most importantly, protons, electrons, and neutrons provide a unifying explanation for the diversity of matter. From the simplest hydrogen atom to the most complex biological molecules, all matter is built from the same basic particles. Differences arise not from different ingredients, but from different combinations and arrangements. This insight reveals a profound simplicity underlying the apparent complexity of the universe. In reflecting on these particles, it becomes clear that they form a delicate balance. Protons provide identity and positive charge, electrons provide interaction and movement, and neutrons provide stability. Together they create atoms that can endure, interact, and evolve. Their interplay explains not only why atoms exist, but also why matter can form structures, store energy, and support life. Understanding protons, electrons, and neutrons is therefore not just a lesson in physics or chemistry, but a window into the fundamental order of the natural world. The origin of electric charge is one of the most fundamental and intriguing questions in science, because it touches the very foundation of how matter behaves and interacts. Electric charge is not something that atoms acquire later in their existence. It is an intrinsic property of the particles that make up atoms. To understand where electric charge comes from, scientists look beyond visible matter and focus on the basic building blocks of nature and the laws that govern them. At the most basic level, electric charge arises from subatomic particles, primarily protons and electrons. Protons carry a positive charge, while electrons carry a negative charge of exactly the same magnitude. This equality is not a coincidence. It is one of the fundamental symmetries of nature. The fact that these charges balance so precisely allows atoms to exist in stable, neutral forms when the number of protons and electrons is equal. The origin of charge, therefore, is deeply connected to the existence of these particles themselves. Electric charge is considered a fundamental property, meaning it cannot be broken down into simpler components. Just as mass describes how much matter a particle has, charge describes how it participates in electromagnetic interactions. Scientists do not explain charge as being made of something else. Instead, they accept it as a basic feature of reality that can be measured, observed, and mathematically described. This places electric charge alongside other fundamental properties such as spin and mass. The concept of charge became clearer as scientists studied electricity and magnetism. Early observations showed that certain materials could attract or repel one another after being rubbed. This behavior led to the idea that there were two types of electric charge, later named positive and negative. While these names are arbitrary, the distinction is essential. Like charges repel each other, and opposite charges attract. This simple rule explains a vast range of physical phenomena, from the structure of atoms to the behavior of electrical circuits. The deeper origin of electric charge lies in the framework of fundamental forces. Electric charge is the source of the electromagnetic force, one of the four fundamental forces of nature. This force governs how charged particles interact with one another. When two charged particles are near each other, they exert forces that can attract or repel, depending on the type of charge they carry. These interactions are mediated by particles called photons, which carry electromagnetic energy between charged particles. From a modern physics perspective, electric charge is linked to the way particles interact with electromagnetic fields. An electromagnetic field is a region of space where charged particles experience forces. Particles with electric charge respond to these fields, while neutral particles do not. This interaction is not random. It follows precise mathematical laws that have been confirmed through countless experiments. The consistency of these laws suggests that electric charge is a deeply rooted feature of the universe. One of the most remarkable aspects of electric charge is its quantization. Charge does not exist in arbitrary amounts, it comes in discrete units. The smallest unit of electric charge observed in nature is the charge of an electron or proton. All other charges are whole number multiples of this basic unit. This quantization suggests that charge is not a continuous substance, but a property tied to the existence of specific particles. This discovery was crucial in advancing atomic theory and understanding the structure of matter. The origin of electric charge is also connected to symmetry principles in physics. Modern theories suggest that charge arises from fundamental symmetries in the laws of nature. These symmetries dictate how particles behave and interact. When a symmetry exists, certain properties, like charge, must be conserved. This is why electric charge is always conserved in physical processes. Charge can move from one object to another, but it cannot be created or destroyed. This conservation law points to a deep and universal origin of charge. At the atomic level, electric charge explains why atoms hold together. The positive charge of the nucleus attracts the negative electrons, creating a stable structure. Without electric charge, there would be no attraction between the nucleus and electrons, and atoms could not exist. This means that the origin of charge is directly linked to the existence of matter itself. Every solid object, liquid, and gas owes its structure to the presence of electric charge. Electric charge also plays a central role in chemical behavior. When atoms interact to form molecules, it is the electrical attraction and repulsion between charged particles that determines how bonds form. Electrons may be shared or transferred between atoms, leading to different types of chemical bonds. These processes are all governed by the rules of electric charge, showing that chemistry is, at its core, an application of electromagnetic interactions. From a broader perspective, the origin of electric charge is tied to the early universe. Shortly after the Big Bang, the universe was extremely hot and dense, filled with elementary particles. As the universe cooled, particles like protons and electrons formed and acquired their characteristic properties, including electric charge. The fact that positive and negative charges formed in equal amounts ensured that the universe remained largely electrically neutral on large scales. This balance was essential for the formation of atoms, stars, and galaxies. Electric charge is also responsible for many everyday phenomena. The sensation of static electricity, the flow of current in wires, and the functioning of electronic devices all rely on the movement of charged particles. These familiar experiences are direct consequences of a property that originates at the subatomic level. The same charge that holds atoms together also powers modern civilization. Despite its importance, The ultimate reason why particles have charge remains one of the deepest questions in physics. While scientists can describe how charge behaves with incredible accuracy, explaining why it exists at all is still an open question. Some advanced theories attempt to link charge to deeper structures of space and time, or to unified forces that existed in the early universe. These ideas are still being explored and tested. What is clear, however, is that electric charge is not accidental or superficial. It is a fundamental feature of the universe that shapes the behavior of matter at every scale. From the smallest particles to the largest cosmic structures, electric charge governs interactions, enables stability, and allows complexity to emerge. Understanding the origin of electric charge is therefore not just about atoms. It is about understanding why the universe is capable of forming structure, energy, and life itself. This deep connection between charge and existence highlights why the study of electric charge has been central to scientific progress. By uncovering how charge operates and where it comes from, scientists have been able to explain atomic structure, develop powerful technologies, and explore the universe in unprecedented ways. The origin of electric charge remains a profound mystery, but it is also one of the most powerful ideas ever discovered in the quest to understand matter and reality. The implications of the origin of electric charge become even more profound when we consider how this property shapes the behavior of matter across different scales of existence. Electric charge is not merely a microscopic feature confined to atoms. It is a guiding principle that influences the organization of matter, the flow of energy, and the interactions that give rise to complex systems. Its effects extend from the smallest particles to the largest structures in the universe, revealing its foundational role in reality. One of the most important consequences of electric charge is its role in creating order. Because opposite charges attract and like charges repel, particles naturally arrange themselves into stable configurations. This simple rule leads to the formation of atoms, where negatively charged electrons remain bound to positively charged nuclei. It also allows atoms to interact with one another in predictable ways, forming molecules and larger structures. Without electric charge, particles would not experience these organizing forces, and matter would remain chaotic and diffuse. Electric charge also explains the transfer and storage of energy. When charged particles move, they carry energy with them. This movement is the basis of electric current, which powers nearly all modern technology. From lighting homes to running computers, the controlled motion of electrons allows energy to be transported efficiently over long distances. This practical application of electric charge demonstrates how a fundamental property of particles has been harnessed to transform human civilization. In materials, the origin of electric charge determines their physical properties. Conductors, such as metals, allow electrons to move freely because their atomic structures provide loosely bound electrons. Insulators, by contrast, hold their electrons tightly, preventing easy movement. Semiconductors fall between these two extremes, and their behavior can be finely controlled by adding small amounts of impurities. This control is only possible because electric charge responds predictably to changes in atomic structure, making modern electronics feasible. Electric charge is also central to biological systems. The human nervous system relies on the movement of charged ions across cell membranes to transmit signals. Muscles contract due to electrical impulses, and the heartbeat itself is regulated by carefully timed flows of charged particles. These processes show that electric charge is not only a physical concept, but also a biological necessity. Life depends on the precise control of charged particles within cells and tissues. On a larger scale, electric charge influences natural phenomena in the environment. Lightning occurs when large imbalances of charge build up between clouds and the ground, releasing energy in a sudden discharge. Static electricity, though less dramatic, is another example of charge imbalance made visible. Even weather patterns and atmospheric chemistry are influenced by charged particles interacting within Earth's electric and magnetic fields. In astrophysics, electric charge plays a subtle but essential role. While large celestial bodies are generally electrically neutral, charged particles are abundant in space. Plasma, a state of matter consisting of free charged particles, dominates stars, nebulae, and interstellar space. The behavior of plasma is governed by electromagnetic forces, which shape solar flares, cosmic radiation, and the dynamics of galaxies. Understanding electric charge allows scientists to explain how stars generate energy and how cosmic structures evolve. The conservation of electric charge further emphasizes its deep origin. In every known physical process, the total amount of charge remains constant. This rule holds true in chemical reactions, nuclear reactions, and particle interactions. Charge may shift from one particle to another, but it is never lost or created from nothing. This conservation suggests that electric charge is woven into the fundamental laws of the universe, providing consistency and predictability to natural processes. Electric charge also serves as a bridge between classical physics and modern theories. Classical laws describe how charged objects behave at everyday scales, while quantum theory explains charge at the level of particles and fields. Advanced theories seek to unify electric charge with other fundamental properties and forces, suggesting that charge may arise from deeper principles of symmetry and interaction. Although these theories are still developing, they highlight how central electric charge is to understanding the universe at its most fundamental level. Philosophically, the origin of electric charge challenges our understanding of explanation itself. Science can describe how charge behaves and how it influences matter with extraordinary precision, yet the question of why charge exists remains open. This does not weaken scientific knowledge. Instead, it points to the depth of reality and the limits of current understanding. Electric charge stands as an example of a fundamental feature that shapes everything else, even if its ultimate origin remains mysterious. In reflecting on electric charge, it becomes clear that it is far more than a technical concept in physics. It is a unifying principle that connects matter, energy, life, and the cosmos. From binding atoms to powering stars, electric charge enables the structures and processes that define existence. By exploring its origin and implications, we gain insight not only into atoms, but into the underlying order of the universe itself. The balance and imbalance of charges is a fundamental concept that explains how matter behaves, interacts, and changes. At its core, this idea is rooted in the way positive and negative charges coexist and influence one another. In most natural situations, matter tends toward balance, where positive and negative charges cancel each other out. This balanced state is known as electrical neutrality, and it is the reason why most objects around us do not normally exhibit noticeable electrical effects. However, when this balance is disturbed, powerful and often visible phenomena emerge. In an atom, balance is achieved when the number of positively charged protons in the nucleus is equal to the number of negatively charged electrons surrounding it. In this state, the atom has no overall electric charge. This balance is remarkably stable and allows atoms to exist without constantly attracting or repelling other atoms electrically. It is this neutrality that makes matter calm and predictable under ordinary conditions. Solids hold their shape, liquids flow smoothly, and gases spread evenly, all because charges within atoms are largely balanced. Imbalance occurs when this equality between positive and negative charges is disrupted. This usually happens when electrons move from one atom or object to another. Because electrons are much lighter and more mobile than protons, they are the primary carriers of charge imbalance. When an atom loses one or more electrons, it becomes positively charged, and when it gains extra electrons, it becomes negatively charged. These charged atoms, known as ions, behave very differently from neutral atoms and play essential roles in both physical and chemical processes. The effects of charge imbalance are evident in everyday life. Static electricity is one of the simplest examples. When certain materials are rubbed together, electrons are transferred from one surface to another. One object ends up with an excess of electrons, while the other has a deficiency. This imbalance creates an electric force that can attract small objects, produce sparks, or cause a mild shock when the charge suddenly redistributes. These familiar experiences are direct results of disrupted charge balance. In chemical systems, balance and imbalance of charges determine how substances react. Many chemical reactions involve the transfer of electrons between atoms. When electrons move, charges become unbalanced, leading to attraction between oppositely charged ions. This attraction forms ionic bonds, which hold compounds like salt together. Even in covalent bonds, where electrons are shared rather than transferred, slight imbalances in charge can occur, influencing the shape and behavior of molecules. These subtle charge differences are crucial for complex chemistry, including the reactions that sustain life. Biological systems rely heavily on controlled charge imbalance. In the human body, nerve signals are transmitted through the movement of charged ions across cell membranes. At rest, nerve cells maintain a carefully balanced distribution of charges. When a signal is sent, this balance briefly shifts, creating an electrical impulse that travels along the nerve. Muscles contract, thoughts form, and senses operate because the body can precisely manage when and where charge imbalances occur. On a larger scale, imbalance of charge can release enormous amounts of energy. Lightning is a dramatic example. Within storm clouds, collisions between particles cause charges to separate, creating large regions of positive and negative charge. When the imbalance becomes too great, the system seeks balance through a sudden discharge. The resulting flash of lightning is nature's way of restoring electrical equilibrium. Similar principles apply in electrical systems designed by humans, where controlled imbalances drive currents through circuits to perform work. Despite the power of imbalance, nature consistently seeks balance. Charges tend to move in ways that restore neutrality, whether through the flow of electrons, chemical reactions, or electrical discharges. This tendency toward balance is a key reason why electric charge is conserved. Charge is not created or destroyed, it is merely redistributed. Every imbalance exists because of a corresponding imbalance elsewhere, maintaining the overall consistency of the system. The balance and imbalance of charges also explain why matter can be both stable and dynamic. Balance provides stability, allowing structures to persist over time. Imbalance provides change, enabling motion, reactions, and energy transfer. Without balance, matter would be chaotic and unstable. Without imbalance, nothing would happen. It is the interplay between these two states that allows the universe to function as it does. Ultimately, the concept of balance and imbalance of charges reveals a deep principle of nature. It shows how simple rules governing tiny particles can lead to complex behaviors and powerful phenomena. From the quiet stability of neutral atoms to the dramatic energy of lightning and life itself, the movement between balance and imbalance of charge shapes the physical world in profound and essential ways. The role of electrons in charging atoms is central to understanding why matter can become electrically charged and how electrical phenomena arise. Electrons are the most mobile of the subatomic particles, and this mobility gives them a unique influence over the electrical state of atoms and objects. While protons remain fixed within the nucleus and neutrons remain neutral, electrons move, shift, and transfer, making them the primary agents responsible for charging atoms. In a neutral atom, the number of electrons exactly matches the number of protons, resulting in no overall charge. This balance is stable under ordinary conditions, but it is not permanent. Electrons occupy regions around the nucleus where they are held by the attractive force of the positively charged protons. However, the strength of this attraction varies depending on how far the electrons are from the nucleus and how the atom's electron structure is arranged. Electrons in the outermost regions are held less tightly and are more easily influenced by external forces. When energy is applied to an atom, electrons may gain enough energy to move to a different atom or escape altogether. This energy can come from friction, heat, light, or an electric field. When an atom loses one or more electrons, it becomes positively charged because it now has more protons than electrons. Conversely, when an atom gains extra electrons, it becomes negatively charged. In both cases, the change in charge occurs solely because of electron movement, not because the nucleus itself has changed. This electron transfer explains many common charging processes. When two different materials come into contact and are then separated, electrons may move from one material to the other depending on how strongly each material holds onto its electrons. One material ends up with an excess of electrons, while the other has a shortage. This process is responsible for static electricity, such as when a balloon sticks to a wall or hair stands on end after being rubbed. Electrons also play a crucial role in chemical bonding and reactions. In some reactions, electrons are transferred completely from one atom to another, creating charged ions that attract each other. In other reactions, electrons are shared between atoms, forming stable molecules. Even in shared arrangements, electrons are often pulled more strongly toward one atom than another, creating partial charges. These slight imbalances influence molecular shape, reactivity, and interactions, showing how electron behavior governs chemical properties. In solid materials, the role of electrons extends beyond individual atoms. In metals, some electrons are not strongly bound to any one atom and can move freely through the material. These free electrons allow metals to conduct electricity. When a voltage is applied, electrons drift through the metal, carrying charge from one place to another. This movement of electrons is the basis of electric current and is essential for electrical and electronic technology. In contrast, in insulating materials, electrons are tightly bound to their atoms and cannot move freely. As a result, these materials do not conduct electricity easily. Semiconductors occupy a middle ground where electron movement can be carefully controlled. By manipulating electron behavior in semiconductors, humans have developed transistors, microchips, and modern computing devices. Once again, the key factor is how electrons behave within atomic structures. Electrons are also responsible for the formation of ions in biological systems. In living cells, charged atoms and molecules move across membranes, creating electrical signals. Nerve impulses depend on the controlled movement of electrons and ions, allowing information to travel rapidly through the body. The heart's rhythm, muscle movement, and brain activity all rely on electron-driven charge changes at the atomic and molecular level. The behavior of electrons also explains why atoms tend to seek stable charge states. Atoms often lose or gain electrons to achieve a more stable electron arrangement. This tendency drives chemical reactions and influences how elements interact. The desire for stability is not a conscious goal but a natural result of how electrons respond to electric forces and energy levels. Ultimately, electrons are the key to understanding charging because they are both charged and mobile. Their small mass allows them to respond quickly to forces, and their negative charge allows them to create imbalances that lead to attraction, repulsion, and energy transfer. Without electrons, atoms would be static and unchanging, and electrical phenomena would not exist. The role of electrons in charging atoms reveals how a tiny particle can have enormous influence. By moving between atoms and responding to energy, electrons enable everything from static sparks to advanced technology and biological life. Through their behavior, electrons transform neutral matter into charged systems, making them essential to the dynamic nature of the physical world. Everyday examples of atomic charge reveal how deeply the behavior of tiny particles influences our daily experiences, often in ways we barely notice. Although atoms and their charges are invisible to the human eye, their effects are constantly at work in the world around us. From simple household activities to natural phenomena, atomic charge helps explain many common events that might otherwise seem mysterious. One of the most familiar examples of atomic charge in everyday life is static electricity. When you rub a balloon against your hair or shuffle your feet across a carpet, electrons are transferred from one surface to another. This movement of electrons creates an imbalance of charge. The balloon may gain extra electrons and become negatively charged, while your hair loses electrons and becomes positively charged. As a result, your hair strands repel each other and stand up, while the balloon sticks to walls or ceilings. These effects occur because opposite charges attract, and like charges repel. Small electric shocks are another everyday reminder of atomic charge. Touching a metal doorknob after walking across a carpet can result in a sudden spark. This happens because your body accumulates excess electrons, and when you touch a conductor, the electrons quickly move to restore balance. The spark is the visible and sometimes painful release of stored electrical energy as charges redistribute. Household appliances rely on atomic charge to function. When you turn on a light, electrons move through wires, creating an electric current. This flow of electrons transfers energy to the bulb, causing it to produce light. The same principle applies to televisions, refrigerators, and mobile phones. In all these devices, carefully controlled movement of electrons allows electrical energy to be converted into useful forms such as light, sound, or motion. Batteries are another common example of how atomic charge operates in daily life. Inside a battery, chemical reactions cause electrons to move from one material to another. This movement creates a potential difference, or voltage, which pushes electrons through a circuit when the battery is connected to a device. The flow of electrons powers everything from remote controls to cars, all because of charge imbalances created and managed at the atomic level. Natural phenomena also demonstrate the power of atomic charge. Lightning is one of the most dramatic examples. Inside storm clouds, collisions between particles cause charges to separate, with positive charges accumulating in one region and negative charges in another. When the imbalance becomes too great, a massive discharge occurs between the cloud and the ground or between clouds. The bright flash and thunderous sound of lightning are the result of enormous numbers of electrons rapidly moving to restore balance. Even on a smaller scale, atomic charge affects how objects behave around us. Dust particles stick to screens and surfaces because of electric charges. When a surface becomes charged, it can attract tiny neutral particles by inducing charge imbalances within them. This is why electronic screens often attract dust and why certain materials seem to cling together without any obvious glue. Atomic charge also plays a role in everyday chemistry. When salt dissolves in water, it breaks apart into charged particles called ions. These ions move freely in the solution, allowing salt water to conduct electricity. This principle is used in various applications, including water purification, electrolysis, and even biological processes within the human body. The human body itself depends on atomic charge for normal functioning. Nerve cells transmit signals using electrical impulses created by the movement of charged ions across cell membranes. Muscles contract when electrical signals trigger the movement of charged particles within muscle fibers. The beating of the heart is controlled by rhythmic electrical signals that rely on carefully balanced atomic charges. These processes happen constantly and automatically, demonstrating how deeply atomic charge is embedded in life. Everyday materials also behave differently because of atomic charge. Some materials, like metals, allow electrons to move freely and are good conductors of electricity. Others, like rubber or plastic, resist electron movement and act as insulators. These differences explain why wires are coated with plastic and why metal objects can carry electric current while wooden objects generally cannot. Even modern technology such as touchscreens depends on atomic charge. When you touch a screen, your finger slightly alters the electric field at the surface. Sensors detect this change and translate it into a command. This interaction between your body's charge and the device's electric field allows you to control complex technology with a simple touch. Through these examples, it becomes clear that atomic charge is not an abstract scientific idea, but a practical reality that shapes everyday life. The movement and balance of charged particles explain simple experiences like static shocks, as well as complex technologies and natural events. Atomic charge connects the invisible world of atoms to the visible world we live in, showing that even the smallest particles can have powerful and lasting effects on our daily experiences. The importance of atomic charges in matter lies in their ability to govern how matter exists, interacts, and changes. Atomic charges are not minor details of atomic structure, they are the driving force behind nearly all physical, chemical, and biological processes. Without atomic charges, matter would lack structure, interaction, and energy transfer, making the universe a vastly different and far less complex place. At the most basic level, atomic charges allow atoms to exist as stable units. The attraction between the positively charged nucleus and negatively charged electrons holds atoms together. This electric attraction prevents electrons from drifting away and keeps matter intact. Without this balance of charges, atoms would not form, and the concept of matter as we know it would cease to exist. Every solid object, liquid, and gas depends on this fundamental interaction. Atomic charges also determine how atoms interact with one another. Chemical bonding is essentially an interaction between charged particles. Whether atoms share electrons, transfer them, or partially attract one another through uneven charge distribution, these processes are all governed by electric forces. The vast diversity of chemical compounds, from simple water molecules to complex proteins, arises because atomic charges allow atoms to combine in countless ways. The physical properties of materials are deeply influenced by atomic charges. Conductivity, hardness, flexibility, and melting points all depend on how charged particles are arranged and how easily electrons can move. Metals conduct electricity because their electrons can move freely, while insulators resist electrical flow because their electrons are tightly bound. These differences shape how materials are used in construction, technology, and daily life. Atomic charges are also essential for energy storage and transfer. Electrical energy exists because of the movement of charged particles. Batteries, generators, and power grids all rely on controlled charge movement to deliver energy where it is needed. On a natural scale, the energy produced by the sun and other stars originates from processes that ultimately depend on charged particles interacting under extreme conditions. Atomic charge, therefore, is central to both natural and human-made energy systems. In living systems, atomic charges make life possible. Biological processes rely on the movement of charged ions and electrons. Nerve impulses, muscle contractions, and the transport of substances across cell membranes all depend on electrical signals. Even the chemistry of life, including digestion and metabolism, is governed by charge interactions between molecules. The complexity and adaptability of life are rooted in the precise control of atomic charges. Atomic charges also influence how matter responds to external forces. Magnetic and electric fields interact with charged particles, allowing matter to be manipulated in predictable ways. This principle is used in technologies such as electric motors, medical imaging, and particle accelerators. These applications demonstrate how understanding atomic charge enables humans to control and harness natural forces for practical purposes. On a larger scale, atomic charges play a role in shaping the universe. Although most large objects are electrically neutral, charged particles are abundant in space. Plasma, made of free charged particles, fills stars and interstellar regions. The behavior of plasma influences star formation, solar activity, and cosmic radiation. Atomic charges, therefore, contribute not only to the structure of matter on Earth, but also to the dynamics of the cosmos. The conservation of atomic charge adds stability and predictability to nature. Charge is never created or destroyed, only transferred. This rule ensures consistency in physical processes and allows scientists to understand and predict how matter will behave. The reliability of this principle underpins scientific laws and technological design. Atomic charges also bridge the gap between different branches of science. They connect physics, chemistry, biology, and engineering through a shared foundation. By understanding how charged particles behave, scientists can explain phenomena across disciplines, from chemical reactions to neural activity and electronic communication. Ultimately, the importance of atomic charges in matter lies in their universality and influence. They are present in every atom, every molecule, and every living system. Through attraction and repulsion, balance and imbalance, atomic charges shape the structure, behavior, and evolution of matter. They transform the invisible world of subatomic particles into the tangible reality we experience, making them one of the most essential elements in understanding the nature of the universe.